Mauricio, Dan up there, and Robin as well. And so Peter's already given a nice introduction probably to my first slide. Oh, not quite the first slide. So really the point of this was to integrate a version of conceptual spaces theory with the compositional distributional semantics that we've had some talks about. So the question is, how can we compose concepts? And to answer that, we want to know how we should represent concepts. Then look at, given that representation, how they can be composed. So we're using conceptual spaces theory, and then going on to integrate this with categorical compositional models. So here's this general program. So we choose a pre-Greek grammar or something like that, and interpret it as a category. We will choose conceptual spaces to form our meaning spaces, and again build a category around that representation that has the right sort of characteristics. In this case it needs to be compact closed in categorical language. Then we interpret the compositional structure via a functor that preserves the necessary structure, and then we have this map going off. Bingo! Okay, so we've had this a couple of times already, but I'll just go through it again really briefly. So in pre-group grammar, we've got these sort of reduction rules. So here, if you've got a P next to a PR, that reduces down to 1. And similarly here, if you've got a PL next to a P, that also reduces down to 1. You construct word types out of whatever alphabet you've got. So we've got nouns and sentences. That's what we care about. And you can take these adjoints as well. So an adjective has the type NL, and what that means is when you, if you put a noun here, noun here, so you have like a red, which is an adjective, together with car, which is a noun, then the N and the NL will cancel out. And a transitive verb has this type, meaning that basically if you put a noun on one side, the subject, and a noun on the other side, the object, then the subject and object will cancel out and give you back a sentence type. And that's what this line across the bottom says. So I don't really need to describe what conceptual spaces are, because obviously Peter's just done that in a completely expert fashion. But yeah, so the main things, we've got the quality dimensions like weight, height, and so on. Convex subsets, we're going to build our category around that constraint. And again, there's this internal structure based on domains. Okay, so we're going to move slightly away from the version of conceptual spaces that we have just heard about, and we're going to talk about convex algebras. So this is a fairly dense slide, but I'll do my best to go through it, and if anyone wants to, like Dan wants to chip in and clarify, then go ahead. So some notation to start off with. Given a set X, we can form a purely formal combination of elements of that set. And to denote this formal combination, we use just this little bra symbol. It doesn't have ket symbol rather. It doesn't have anything to do with vector spaces. It's just a way of sort of thinking about it formally. And so we can make a convex sum of these elements, and then a convex algebra is one of these sets together with a mixing operation which satisfies the following constraints: that if you just do a mixture of one element, you get back the element you started with. So here it's considered formally, and here it's considered actually as itself. And if you take a mixture of a convex sum of a convex sum of elements, then that's the same as taking a mixture of a convex sum of a mixture of the elements. So this sort of flattens out. So examples here are vector spaces. So there, the mixing operation is just what you like, how you think about normally adding together vectors. And we've also got simplices, trees, which could be really useful here. So then a convex relation between two sets with two mixing operations is a relation that that commutes with forming these convex combinations. So effectively, if the individual elements in the set are related, then the mixtures of those elements are also related. So using this idea of a convex algebra, i.e. giving you a way to form convex combinations on a set, we're going to use that to define a category called convex rel, which is basically going to be the category of conceptual spaces that we use. So we have convex algebras as the objects, and the convex relations that we just defined as morphisms between those objects, and composition and identity, sort of standard one. And then this has the necessary categorical structure for what we need. So what we do need here is essentially being able to do these cups and caps that form the grammatical reductions that Bob was talking about. So, and also being able to take the tensor product of two such algebras. So just say that the unit is just the singleton set. The tensor product is the Cartesian product on the two sets, with the mixing operation applied pointwise. The cap basically sends the singleton to the set of pairs where the two elements of the pair are equal to each other, so it's a sort of diagonal set. And then the cup is the converse of that. Okay, so how is this going to work in general? So we're going to define a conceptual space to be an object of convex rel, i.e. one of these convex algebras set with a mixing operation. And what we need is to match the pre-group grammar is a noun space n and a sentence space s. And then we define a noun to be a convex subset of n, and then a sentence is a convex subset of s. So I don't know how that sits with people, but and then the noun space n is also going to be organised into these domains like colour, texture, and so on. So start setting up an example. So a property, so let's say we've got some domains. We're going to have the domain of colour, taste and texture, and we're going to be talking about food and drink defined by colour, taste and texture. So a property, P sub yellow, is just a convex subset of just a domain, not the entire noun space. And so we've got the following examples. So these are specified in hues, saturation, value. So it's this cone we're talking about. And these pick out specific areas of that colour code that correspond to those colours. The properties for taste. So taste we see as being convex combinations of sweet, sour, salt and bitter. Thanks. Sweet, sour, salt and bitter. And so, so this just takes the sort of bit of that space where sweet sort of beats everything else. So some nouns. so the colour coding here, all that's doing is saying, so banana, this is the colour domain of banana, this is the taste domain, and this is the texture domain. So this is a sort of greeny yellow colour, and then a particular sort of set of tastes, and then the texture is fairly soft. Whereas so I've just made up the texture thing. It just goes from 0 to 1. And it's not too important. So texture is fairly soft for banana. For apple, it's a bit harder. And then for beer, it's liquid, obviously. So you've just got a very small bit there. And yeah, and so here's a sort of pictorial like version of that. So here are the banana colours, the apple colours, and so on. Okay, so we also need to define a sentence space. And we see sentences as also being events, but sort of slightly less structured events than Peter was talking about. So, yeah, we've got events can either be positive or negative, or they can be surprising or unsurprising. And we just have a sentence space of pairs. So the first element states whether it's positive or negative, and the second whether it's surprising or unsurprising. And we can form a convex structure on this by treating it as a lattice. And the mixing operation is taking max, element-wise max. So sentence meaning is a convex subset of the space. So you can have singletons, so you can say something's negative and surprising, or you can just have larger subsets, so this would be negative, because it's negative and either surprising or unsurprising. So for adjectives, in pre-group grammar, the adjective type is n left adjoint. So in convex rel, it's in the noun space tensed with the noun space. And here, so what I'm going to do here is contrast two types of adjectives, where you have intersective adjectives, where they're sort of very easy, and you just take the intersection of two nouns, essentially, versus non-intersective adjectives, which are a little bit more complicated. So we've translated, so what's happening here is that we can actually see that if we take just a noun, a sort of noun version of yellow, and intersect it with banana, this the little Frobenius dot here, and functions as intersection. We then manipulate the diagrams a bit. We can see that this will represent yellow as this sort of very simple structure here, and this explains why we've got this intersective adjective property going on. In the case of soft, the elements that belong to the adjective soft depend on whether you're talking about bananas or apples, for example. So you've got these correlations between the domains, between essentially the colour domain and texture domain. So instead of being able to do this sort of decomposition into something like this, we just have to think of soft as being a relation. And again, we can rewrite it so that we kind of have this, so that we can see it as being the right sort of, having the right type in the pre-group grammar. So for verbs, again, in this category, we're going to have noun space tensed with sentence space, tensed with noun space. And then I'm going to talk about the taste space. So here, I've used words like green banana as shorthand. You can sort of write that out in longhand with all the sort of elements that would go in there. And you can also, it wouldn't necessarily be green banana. You could have all sorts of different correlations going on within this space. But here, so this, the meaning of taste sort of maps some nouns. So I'm just restricted to bananas and beer here. I'm not talking about the taste of apples. So this basically maps pairs of nouns into the sentence space. And we'll see what happens when we do that. So we can form sentences and apply the grammatical reductions. So we've got this product of bananas taste sweet, and we apply this this epsilon map here, which does a cup between sweet and the latter bit of taste. So it's doing a cup. So if you imagine you've got sweet over here, and it's matching to each of these elements here. And what it picks out, as you can see, it's going to remove the bitter ones, and it will pick out just the sweet ones. That's how this cup functions. Then again we've got banana. Again we draw a cup between banana and the green banana and yellow banana. Both of those are in fact bananas. And so what we're left with is this 1, 1, 1, 0, which is positive. So the meaning of this sentence in this very simple toy example is that bananas taste sweet is positive. However, controversially, sweet beer is negative and surprising. So we don't really want beer to taste sweet, and we don't expect it to. So relative pronouns, I think people have talked about this a little bit. This is a drawing of how the fruit which tastes bitter looks in the grammar, and what happens if we do these reductions is that we get fruit that tastes bitter is green banana. So this allows us to do definitions, give meanings to new words even. Okay, so that's all I wanted to introduce to you about it today. In summary, we've applied the scheme to conceptual spaces. We've developed this category, convex rel, which describes, which gives the right sort of structure to conceptual spaces. We can represent different parts of speech and sentences, and we've demonstrated it with a number of toy examples. So there's loads to do still, obviously. So within the category we've developed, there isn't really a distance measure built in. I mean, if you're using vector spaces, that's got a distance measure in it, so we can use that. But you might want to use other sorts of structures like lattices, trees, and so on. It would be useful to have notions of convergence and fixed points to talk about dialogue between agents and how they can negotiate meanings. So connected with that, we'd like to get some betweenness relations going on instead of just this convex mixing. And there's also ideas about negation and other logical connectives, which we don't have yet. So, thank you.
So I think for a start this is a fantastic piece of work. It's lovely to see some people really trying to unify things, just carrying on with their own idea. Do you have any intuitions for how the kinds of structures that you're going to be working with here, not the mathematical operations you can apply to them, but the actual structures themselves, are going to relate to the more standard distributional semantics models?
So I think the key thing is, like, say with the standard distributional semantics model, you build it out of text corpora, and there isn't really a massive amount of structure on the dimensions that you're building. Here you are choosing specific, special dimensions. So if there were a way of doing that within a distributional semantics model, and just sort of saying, okay, I'm going to build a conceptual space from a corpus, but just concentrate on these specific structures, that might be one way of sort of unifying the two.
I have two comments I have three comments.
Okay.
One question. The first comment is I think this is a wonderful program.
Oh, there's many people here.
Okay, but it's great. Second comment is that I think you should replace N and S with a richer set of starting categories.
Oh yeah.
And
Okay.
third comment, I think you should replace sentences with a richer type as well. And I think that the analysis I gave of an event could give you some idea of what.
Yeah, it's just got more structure in it.
My small question is concerns. Why do you really want to do this distinction between intersective and non-intersective adjectives? I mean, basically, intersective adjectives are very rare, and that's a remainder from old logic. I mean,
sure.
Even color words are very much intersecting. I mean, red wine, red hair is the same as a red book.
I think so it's not a really important part of it. I mean, most of them are going to be of this sort of form. But I just thought it was interesting that actually you could provide an analysis of what's going on within this string diagram formalisation, which looks quite nice to me.
But I think there was a question there first.
Well, mine does sort of follow actually a little bit. To follow from the more complex set of sentences, what's noticeable about the sentences you've discussed is they're all sort of basic Aristotelian predicate assertions, like soft, tasty banana. The banana is soft and tasty. So you could get straight into go from chapter 1 to chapter 2 of on interpretation, and the next thing Aristotle introduces is and a verb is now a noun plus the notion of time.
Okay.
And so the monkey ate the banana, getting to the events. What would a structure for I mean, you can totally shoot from the hip or say we haven't thought about it yet, but what would a structure for the monkey ate the banana look like?
So I was thinking about this in a slightly different thing, where you might have, say, an agent moving from one room to another. You might want to describe that. And there, I mean, I just thought that you could have time as a dimension in your space. So it might go from sort of, you'd have now at the zero axis, and before, now, future, and then maybe you've got your room is just, I don't know, maybe left-hand side of the room to right-hand side of the room or something, and then you can talk about your events as being perhaps lines within that, and so you'd have a sort of convex subset of lines that would form your sentence.
So a bit like the old physics world lines model.
It could be. I don't know much about it, but
it's sort of what you draw.
So something like that. That might be one. That's the sort of this off the top of my head how to incorporate time into things.
We have time for one or two more quick ones. Yeah.
Okay. Just another Applehood question, I guess, or color question. So as we discussed before, colors have this polar structure.
Yeah.
Yeah, and since you're defining an algebra on your objects and not a non-deterministic algebra, it's an actual mixing operation with initial point, another initial point, and p that weights them, and you define a unique intermediate point. On the colors, that seems to be a bit complicated, because for example, if you so you're basically picking a cut, and you're saying I am turning my colors into a rectangle, but then if your cut is along blue, like it seems to be in this case, you get that magenta, and one half mixing of magenta and teal would be yellow, which is not necessarily what you want.
Yeah.
So how have you given some thought to generalizing this mixing operation to a mixing relation, perhaps, that could deal with multiple paths? But is that what the betweenness is?
Anyone else in the group?
Well, we've thought about it, but we haven't solved it.
Yeah.
You don't really want a mixing relation. You don't mean a mixing operation. You want like a ternary in between this.
Yeah, exactly. Basically, it's a p weighted in between this relation.
But basically, the reason that the construction that we've got works is this thing that it's the category of relations on the Eilenberg-Moore category of the finite distribution monad, and that type of trick gives you a compact closed category. And there isn't a similar trick for the between this relations stuff, so we need to be cleverer, and being cleverer is slower than doing that trick.
I see.
So,
Yeah. So this is an extension you're already working on.
we've given it some thought already.
Because that would capture the idea that you have this circle, and then when you take antithetical points, for example, 1/2 might be both blue or yellow, depending on.
It would let us do things like between us in graphs and things like
Yeah.
that, which this mixing operation stuff doesn't let us capture very well.
Okay, thank you.
Time for Ross, please go.
So since Dan already mentioned categories, I can ask this question. So your category is the category of convex relations. So as you might know, the category of linear relations has been totally axiomatized in terms of algebras and Frobenius algebras. Is there any relationship between this category and that category?
I think they come from the same construction, so you do the same thing but with a different monad. You reduce down to a more category and then you do the category of relations on it and you would get Abel's category of linear relations. But then the category of linear relations I think is simpler because there are only effectively 3 vector spaces. So I think that's why you can do that axiomatization of that prop really easily. Whereas in this case there are non-free convex algebras, so it would be harder. So it's a sort of richer place I think.
So you can't just port the theory over.
I don't think you can do that trick. We've given a little bit of thought to that as well.
Thank you.
All right, thanks very much.